Let's examine the algebra of solving limits. Consider a limit of the form limit of some function f of x as x approaches some number a. For example, the limit of the function x squared plus 2 as x approaches negative 1. One of the ways to understand a limit is through a graph. We see that as x approaches negative 1, the corresponding y value is 3. So solving this limit, we evaluate x squared plus 2 at x equals negative 1. This gives 3. Let's consider the limit of x squared minus 25 divided by x minus 5 as x goes to 5. So in this case, if we do a direct substitution and evaluate the function at x equals 5, we get 0 over 0. When we get such a form, we need to factor the expression and cancel out what's giving the 0 over 0. Then we try a direct substitution again. In this case, we get 10. X squared minus 25 divided by x minus 5 simplifies to x plus 5. So this is a linear equation as we see in the graph. There's a hole at x equals 5 because the function was not defined at x equals 5. But the limit as we approach 5 is going to be 10. Now consider the limit of 1 over x minus 1 as x approaches 1. This rational function has a vertical asymptote at x equals 1. So we need to see where the graph is going on either side of the asymptote. So we split this limit and consider the limit as x approaches 1 from the left of 1 over x minus 1 and the limit as x approaches 1 from the right of 1 over x minus 1. As we approach 1 from the left, we see that the graph goes down to negative infinity. And as we approach 1 from the right, we see that the graph goes up to positive infinity. So since the graph is going to different places, then the limit of 1 over x minus 1 as x approaches 1 does not exist, because the one-sided limits are not equal. So in this case, when we do a direct substitution, we get 1 over 0. So whenever we get a non-zero number over 0, then we need to use one-sided limits to determine if the limit exists. Now let's look at limits of the form limit of some function f of x as x approaches either positive infinity or negative infinity. First, consider the limit of k over x as x approaches infinity and the limit of k over x as x approaches negative infinity, where k is any constant. Well, for the first limit, as x gets larger and larger, the value of k over x goes to 0. To see why, just divide some number on your calculator by a really big number. Similarly, choosing x to be a larger and larger negative number for the second limit results in k over x going to 0. So both of these limits equal 0. In fact, the limit of k over x to the n as x goes to positive infinity or negative infinity equals 0 for any constant k and any number n bigger than 0. So we'll keep this fact in mind when solving any limit of the form limit of f of x as x goes to positive or negative infinity, where f of x is a rational function. For example, consider the limit of 3x plus 10 divided by x plus 2 as x goes to infinity. Geometrically, we can see that as x gets larger and larger, the graph approaches the horizontal line y equals 3. So algebraically, how do we manipulate this limit? Well, we can create terms of the form k over x to the n by dividing every term by the highest power of x in the denominator. And we simplify. Any terms of the form k over x to the n will go to 0 as x goes to positive and negative infinity. So we get the answer 3. So another conclusion we can see is that evaluating limits at infinity tells us the value of any horizontal asymptotes, if any exist. Let's evaluate the limit of 3x cubed plus 5x minus 2, all divided by 5x to the fourth plus x cubed plus 3x as x goes to negative infinity. Again, we divide every term by the highest power of x in the denominator. Then we simplify, and all terms of the form k over x to the n go to 0 as x goes to negative infinity. So we get 0 over 5, which equals 0. In general, whenever we have a rational function and the degree of the numerator is smaller than the degree of the denominator, the limit as x goes to infinity or negative infinity will equal 0. Now let's consider the limit of 6x squared plus 4 divided by 3x plus 1 as x goes to infinity. Again, we divide by the highest power of x in the denominator, which in this case is x, and we simplify. Then 4 over x and 1 over x are terms of the form k over x to the n, so those go to 0 as x goes to infinity. But what about 6x? Well, the limit as x goes to infinity of 2x is infinity. In general, when our rational function has a higher degree in the numerator than in the denominator, the limit will be either positive infinity or negative infinity. So there won't be any horizontal asymptotes. Finally, let's consider the limit of f of x as x approaches positive or negative infinity when f of x is a polynomial. For example, 3x cubed minus 10x plus 4. Well, we can equivalently look at the limit of the leading term whenever we're looking at a polynomial. So this limit is equivalent to the limit of 3x cubed as x approaches infinity. This polynomial has odd degree and a positive leading coefficient, and so the graph starts in the third quadrant and ends in the first quadrant. So as x goes to infinity, the graph goes up to positive infinity. Let's look at another example. The limit as x goes to negative infinity of negative 2x to the fourth plus 3x cubed minus 40x plus 1. Again, since f of x is a polynomial, we can equivalently look at the limit of the leading term. So the limit of negative 2x to the fourth as x approaches negative infinity. The degree of this is even, and the leading coefficient is negative. And so this graph starts in quadrant 3 and ends in quadrant 4. So as x goes to negative infinity, the graph goes down to negative infinity.